All right, so hello everyone. I'm Jonatan. I work at Dashbit, and today I want to talk about Livebook. So over the past 4 years, I've been working mostly on Livebook and related projects. And there has been a number of articles and talks where people kind of discuss the use cases for Livebook and what you can do. So my idea for this talk specifically is to talk about implementation specific, some patterns that we use to implement Livebook itself. And I'm kind of assuming you heard or know what Livebook is, but I will give a brief context. So Livebook is a code notebook application where you can write and edit notebook documents. And we started it in 2021 in the advent of Elixir NX, numerical Elixir. And it is kind of our own take on the idea of computational notebooks. Another prominent example would be Jupyter in the Python space. And since we were starting to do machine learning in Elixir, we wanted to have our own tool, which is tailored specifically for Elixir and also uses Elixir for the implementation. So here I have Livebook running. I have it running locally, but it's a web application and it can run in the cloud. There are official Docker images. And so I can go ahead, create a new notebook. This is the main page where users generally interact with the application. Here we can craft a notebook document. So in particular, we can write some Elixir code. You can see there is some IntelliSense. We can run this code, get the result. It's kind of a combination between an editor and an IEX session. Sorry. The font. Oh. All right. And in addition to writing code, we can, for example, document it, create some narratives using Markdown. And yeah, so that's the general idea. Now, there's an important distinction to make, kind of going forward, that notebook document is just like a static document. It's effectively a file, so we can export it, and you can see it's just Markdown, which we can later open inside Livebook. On the other hand, this page that we are looking at, it's called a session, like a live editing session. And it's a kind of ephemeral being where users collaborate on the notebook. Now, let's have a look at some of the pieces that I'll cover in the talk. So we have the browser, which represents this session page. And it's controlled by a LiveView process, since we use LiveView for rendering the content. And there can be multiple users looking at the page, collaborating on the notebook. So there are multiple of those LiveView processes. And all of them communicate with a central session process, which is responsible for kind of orchestrating everything. So the changes to the notebook, distributing the changes back to all of the users. It's also responsible for evaluating the code. You can see tags to runtime server. And that runtime server runs on a separate Elixir process, separate Elixir node. The reason we do that is to isolate that code. So for example, if you run something that crashes the runtime, we don't want Livebook itself to go down. And also, each notebook uses its own set of dependencies. So for isolation, we want to have a separate node. Now, given all this context, the first kind of thing I want to talk about is state synchronization. So if we go back to Livebook, I will open this in another tab. You can imagine it's two separate users. And now you can see that if I make any changes on the left, it automatically synchronizes between all of the users. You can see all the changes. If I do evaluation, all the state is replicated. So the question is, how do we replicate that state? And on the code level, we have this huge session data struct, which in particular holds the notebook, the current version of the document, the static document. And it also holds a lot of extra bookkeeping that we do. So for example, for each cell, we want to store whether it's evaluating, whether it's in the queue. We also track dependencies between cells. So if you define a variable in one cell and then you use it in another, we keep track of the dependency. So if one of those cells changes, we can mark the other one as outdated. So we have all of this state encapsulated in this Elixir struct. And the question is, how do we make this struct be kept in sync between all of the LiveView processes and their central session process? So The synchronization is a common problem in software engineering, and the solution we pick really depends on the system constraints. So in our case, we have processes in the same memory space, same operating system, so we can kind of assume that they are all active online, and the latency to communicate between them is small. We could also deploy Livebook in the cloud with multiple nodes in a cluster distributed deployment. And then we have this extra latency to communicate between those processes. But even then, kind of the properties don't really change because we, again, still kind of assume that the processes are online. This would be opposed to a case where you have the browser and you have local state there, and then you want to synchronize it offline after a while. So what we do with Livebook is we serialize all of the operations. We kind of want to give them a deterministic order. So whenever one of the users make a change, like insert a cell, remove a cell, make some text change, we send operations, here represented as A, B, and C. We send those operations to the central session process, which is going to receive them in a particular order, and is going to distribute those operations to all of the LiveView processes back. And what this gives us is that now, if we take our data structure, we can apply those operations one by one, and everybody will immediately arrive at the correct state. And so how the kind of implementation looks like is we define a set of semantic operations that make sense for our data structure. So for example, inserting, deleting cells, moving cells. And then we define a function that takes our structure, data structure, takes an operation, and it returns an updated operation. This function is pure, so it has like no side effects. One thing to note here is that it can also return error. And in a collaborative environment, error is expected because you can imagine if two users remove the same cell at the same time, the first operation is good, we remove the cell. But the second operation, when it arrives, the cell no longer exists. So we just want to basically ignore that operation as no longer valid. And I mentioned that this function is pure. So the question is, how do we handle side effects like code evaluation? And this needs to be handled by whoever calls this function. So for example, the session process. One way to do it would be to kind of compute the difference between the previous state and the new state and try to apply the necessary side effects, but that's a bit unpractical and inefficient. So what we actually do is we modify this code to also return a list of side effects, such as starting evaluation. And then when the session applies the operation, it receives this side effect, and it dispatches it accordingly. Now, in Livebook, we have like over 60 of those semantic operations, and it's like a huge part of Livebook complexity lives in this module. So we want to, very extensively test it. Here's an example of such an operation. We have our data structure. We want to remove a cell. So we find the cell in the notebook. If the cell is not found, then we want to just return error, ignore the operation. If we find the cell, we just remove it from the notebook, and we update any additional bookkeeping regarding the outdated cells that depend on it. And we return a side effect to kind of clean the runtime state for that cell. So now, again, we have a bunch of those operations, and we want to test them. The good thing about it being a pure function is that we can write very cheap and declarative tests for those operations. And the way usually how this would look is we have a sequence of operations that arrive our state at a certain point. It kind of emulates user making a bunch of interactions with the notebook. And then we just apply a specific operation and see if our state is at a point that we expect. So we have a huge amount of those tests, and they are very cheap to run because, again, there is no side effects. And this way, we kind of validate that all the core logic is robust. So with this, we have everything synchronizing across the users. There is one kind of operation which is a bit more nuanced, which is text editing. And we have two types of text editing. So for example, if we have the title here, we can change the title. And you can see that it's not immediately replicated for the other user. Only once we blur, the change kind of atomically is sent and replaced for both users. So this works for a title because it's kind of an atomic change. Somebody just wants a specific title. The problem is that in the case of the code editor, we may have like a huge amount of code, and two users want to change different parts of that code at the same time. And so this approach of like replacing the whole content doesn't really work because they would overwrite each other. We could fix this by kind of locking the cell for editing as soon as one person starts typing, but there's not really like a good user experience either. So what we actually want to do is for both users to be able to type and then kind of merge those changes so they arrive at the same state. Now, to this problem of text synchronization, there are two usual approaches, which is operational transform, denoted as OT. And it's kind of an older approach, which is an industry standard. It's been used to build Google Docs, for example. And that's also what we went with in Livebook, since it is very established. But it's worth mentioning that there is another approach, CRDT, which stands for conflict-free replicated data types. And that's a much newer approach. It's been kind of actively researched over the last years. And both approaches have different trade-offs. It's just that for like Livebook, the operational transform kind of makes more sense. And I want to give like just a brief idea of how that approach works. So we can imagine we have two users, and they have a text starting on the same state, hello world. User on the left is inserting a new text at the beginning, right? Here's the operation. User on the right is removing the word world. Here, you can see this range. Now, so they have a different state at this point. Now, if we exchange those operations between the users, on the right, we can just prepend this text, very straightforward. And on the left, we need to remove the same range as the other user did. And you can see that in this case, we would actually remove the word hello, which is not what the original user intended, right? We got two different text states as a result. So the idea behind operational transform is that whenever we receive an operation from another user, we want to look at the recent operations that we did locally, and the other user is not aware of them. So in this case, we see this operation, and we transform the incoming operation to account for all of those local changes. So in this case, we would shift the deletion range to the right to account for those newly inserted characters. And then if we take this transformed operation, you can see that we actually remove the word world, which is as the user intended. And this way we arrive at the same state. So the idea is to kind of define those transformations for all possible combinations of editing of text operations. And then we make sure to always transform the operations. This way everybody arrives at the same state. Now, in order to kind of merge this into the solution that I've just described, the synchronization approach, we define a new operation, apply sol delta, where delta is like a diff. It's a sequence of deletions and inserts, like a batch of text editing. So when a user types, we have this diff, we send it to the server. Now the server is going to apply it to the text and also transform it if there are any newer operations already on the server from other users. And so then we emit the side effect report sol delta here, which is going to broadcast the transformed delta to all of the clients directly to the browser. We handle this like with LiveView JavaScript hooks to directly edit modify the editor, the code editor. And yeah, and locally, if there are any more operations in the buffer for a given user, we would further transform that delta so that yeah, it can account for all of the operations. So with that, we basically have all of the synchronization parts covered. That's how we synchronize the state. We have this data in all of the processes, and we just render it with LiveView. All right. The second thing I want to talk about is our use of Phoenix Tracker. So if we go back to Livebook, you can see that on the homepage, we list all of the running sessions. Now, as you could see, a session is just a process, right? It's not something we persist anywhere. It's just a running process. And then like if we go and close the session, the process is gone. It's no longer in the system. And so the question is, how do we track all of those active sessions? And we also want to like show some metadata. So here we show the notebook title, the memory usage, creation time. And again, going back to code, we have like this struct with all of the metadata about the particular process. And so what we want to do is be able to look up those processes by an identifier and also be able to list all of them, kind of as we would do with a database. And so in the Elixir standard library, there is the registry module, which allows you to do basically that, register process under a specific identifier, and then you can look up, you can list all of the processes. Now the problem is that with registry, the information is local to the given node. So if we were to do a distributed deployment with 2 Livebook nodes in the cloud, each node would see only a subset of those session processes, which means we cannot really reliably show them on the home page. So what we actually want is something like Elixir registry, but replicated across all of the cluster. And this is exactly what Phoenix Tracker allows us to do. You can see here's kind of the API correspondence between those 2 modules. Phoenix Tracker module is like a little bit under the radar. You may not exactly heard of it, but it's actually the foundation of Phoenix Presence. And Phoenix Presence is just like a wrapper around Phoenix Tracker with a more convenient API for Phoenix channels. But basically, the foundation is exactly Phoenix Tracker, and it allows you to register a process under a specific key, attach any extra metadata that you want, and all of this information is eventually synchronized across all of the cluster. So let's see how we can use Phoenix Tracker to implement like crude API for our sessions. The first thing we need to do is to implement like init and start link callback, as we would do with a typical gen server. Phoenix Tracker is a behavior, similar one. This is taken straight from the Phoenix Tracker docs. There's really nothing fancy here. We just pass the pub server as an option, and that's the name of our pub/sub process running under supervision tree. In this case, it would be livebook.pubsub when we started. The more interesting part is our higher level API. So for example, if we start a session, and now we want to insert it into the tracker, kind of make it visible in the list, we call Phoenix Tracker truck. We specify the tracker process name that we would start. We can have like a constant name that we use in this case. We specify the process that we want to track. Also a topic. We can have multiple groups of processes in the tracker. In this case, we just have this group of sessions. Then we have the identifier, which is going to be used for looking up those processes in the tracker. And as part of metadata, we store the whole session struct with all the information. So for example, then we can list all of those session processes. And from the metadata, we can extract our struct, the session struct. There is one more callback that we implement for the tracker, which is handle_diff. And this one is called whenever a new process enters the tracker or terminates, and whenever it happens on a current node or in a remote node that is connected to us. So we use this callback specifically to broadcast messages in our application. So for example, when a process leaves the tracker, we are going to broadcast the session closed event. And then on the home page, in the list of sessions, if one of the sessions is closed, we can immediately update the list so it's already doesn't contain that session without refreshing. The only nuance here is that if we update metadata for the given process, it's treated as a process leave and join. So you can see here that for all the joins, if there is a corresponding leave already, we actually want to treat it as an update. And with this, our higher level API looks like this. We can track session process. Here's our struct. And this also is going to broadcast this message in the system that the session was created. We have the same for updating a session. And then whenever the process terminates, either normally because we closed it, or abnormally because there is some crash, it disappears from the tracker and we broadcast this event in the system. And then we can list and fetch session as we would in a database, basically. And there is one more nuance, which is that when we register a process, we track a process on one node, it's not immediately visible on another. So it may take like 2 seconds for the state to synchronize. And this can lead to subtle race conditions. So for example, if we open an existing notebook, it creates a new session. You can see here. And if that notebook has an image, it may not be visible on the screen, but basically the URL of that image also points to a session, and this is a separate request that goes and hits a regular controller. So now you can imagine we opens this session on one node, but now we load the image and it hits a different node through the load balancer. And so if that other node is not yet aware of that session, the request would fail. So what we want to actually do, that's what we do in Livebook. We fetch the session from the local tracker. If it's available, then it's all good. We just return it. And if we fail to find it, then for the given ID, we want to figure out which node session with this ID is running. And then we do an RPC call to ask the tracker at that specific node to give us the information. Now, the question is, how do we know, based on an identifier, which node should be talked to? And that's what we do. So whenever we start a new session, we generate an ID. And as part of this ID, we include the hash of the node name, and also some random bytes because we use random IDs. And then in order to find which node a particular ID belongs to, we just take the list of all the nodes that we are connected to, and we kind of brute force find the one with the matching hash. The good part about it being a hash is that we don't expose the node name, and also the ID size is fixed, because regardless the node name length, we have this hash of 16 bytes. All right, and the third part I want to cover is remote runtime. So in Livebook, as I mentioned, we run the code in a separate Elixir node. And by default, we would just start a separate Elixir process on your local machine. However, we also have this feature where you can configure a Fly.io machine as a runtime, or a Kubernetes pod where you just put your Kubernetes configuration. And what happens here, so for example, in the Fly case, we would dynamically spawn a machine whenever you want to evaluate code. And then we would evaluate code on that particular machine. When you terminate the runtime, we just kill the machine. And the same with Kubernetes. We start a pod anywhere in the cluster that you configure. And it's temporary for this specific use case. What's particularly kind of appealing about this is that you may use a machine or a Kubernetes pod with a GPU, even if you don't have a local one. And this way you can run some more expensive machine learning computations. So before kind of diving into how this works, let's first discuss how connecting to a distributed node works. So when we would call node connect and give it a node name, the node name has two parts, the base name in the blue, and then a host name, which can be either an IP or a domain name. So the first step is that we need to find the IP, which machine we need to talk to. And again, if it's an IP, it's good. If it's a domain name, we need to ask the DNS to resolve that, and this way we obtain it. And then we know, OK, at this machine, we have an Elixir node running. Now, when an Elixir node starts in distributed mode, it's going to listen for distributed connection on certain port. By default, that port will be random. So here you can see we have port 7000. And then what Erlang does is it also runs this separate operating system process called EPMD, which is like a tiny server on a fixed port. And this server maintains a mapping between the node name of all the local nodes on that machine into the distribution port. So now, once we know the IP of the machine, we can go to that machine and talk specifically to the EPMD, because it's a fixed port that we know. And we ask it, what is the port, the distribution port of this node, right? We get the port back, and now we have the IP, the port, and we can establish the distribution connection into that port. So now going back to the remote runtime, we have our Fly machine running in the cloud. And the problem is that we cannot really directly connect to it from our local machine because it's running in a private network. And we don't necessarily want to make all of the ports public on that machine, right? What we could do is install, what Fly allows us to do is install WireGuard, configure it as a VPN, and then we can actually directly talk to the machine. The problem is that for Livebook, it's not really a good user experience to go and say, oh, you need to set up WireGuard, install all of the configuration. So what we do instead is we start a proxy. So we open a tunnel from the remote machine, the distribution port. We tunnel it into a local port. And the only thing to do that, the only thing we need is an access token. And the token we need anyway to start the machine. So this way we have this distribution port available locally. What's even better is that Kubernetes CLI also has this option, so we can kind of use the same approach for both. And so we have this local port that we can talk through the distribution. The question is, how do we make Erlang connect to that local port? So going back to the diagram, how do we make the step 1 and 2 be something else, like we want to customize it? And Erlang has this feature, not necessarily very well known, but we can implement a behavior. It's not formally a behavior, but it's a module with callbacks, so effectively it's a behavior. And we can configure exactly those steps. So here's the first callback we are interested in, address please. We are given a node name, and we need to resolve which IP address we want to talk to. So we can special case that for all of the nodes that are the runtime, the remote runtime, we just return loopback, so it targets our local machine. And for the second one, the second step, we need to find the distribution port. So here, what we actually do is we include the port as part of the node name. So this port is the same local port that we use for tunneling. And that's something we can do in Livebook, but you can imagine we could also fetch this information from ETS table or similar. And so by customizing those steps, now we can successfully connect. When we call the node connect here, it would, instead of going through those steps, it would just connect to the local distribution port, and we can talk to the remote machine. And once we define this module, there are two ways we can use it. We can either specify a VM configuration at boot. So here's an example with Elixir releases. Or we can configure it at runtime, but this needs to happen before the Erlang distribution starts. So if we go with this approach, we need to start the distribution programmatically at runtime as well. And those are the three parts. I see you have a bit of time, so there are a few kind of smaller things I want to mention, which may be worth and interesting. First of all, you can see that in Livebook we have this code editor. If you search online, there are two main code editors for the web. The first one is Monaco, which is extracted from VS Code. It's very feature-rich, a lot of IntelliSense kind of features that you can enable. But also it's very heavy and complex. And then there is Code Mirror, which is implemented from scratch specifically for the web. And when we started Livebook, Code Mirror was in the process of entire rewrite into a new major version, into a new design. So we went with Monaco. But like a year ago, I read a few articles that kind of motivated me to have another look at Code Mirror, at the new version, and I decided to migrate. And I just want to share that the experience is like extremely positive. Code Mirror is very extensible and modular, so you can literally start with a plain text area and then keep listing extensions until you basically get the full IDE. You do need to implement some of the IntelliSense features yourself, but there are building blocks, and that part was not really challenging. What's cool is that once you wrap your head around the abstractions that Code Mirror provides, you can basically write any kind of extension, and it's very fun to do so. It has a fantastic documentation, both API reference and conceptual guides. Styling is very easy. The author is very responsive to requests. And the funny part is that the main work that I had to do as part of the migration was to implement Elixir syntax support for Code Mirror properly. And the funny part is that we did this for Monaco before as well. But as a side effect, now both editors have good Elixir support. So it's kind of a nice thing as a result of that. And in Livebook, you can run the Livebook itself behind authentication proxy like Cloudflare, Google, or Tilescale. And we have this configuration where we can fetch information about the user from the request metadata, and then we like show it in the user. For each user collaborating, we kind of fill this information automatically, and you can also access that information from the notebook itself. So we have those modules which kind of encapsulate this logic for extracting user information from the request, and we may even like extract into a separate library in the future, but my point is that if you have a use case for running your app behind a proxy, you may want to look at those modules because you can just directly use them in your plug. Also, we have this server-side, server-driven confirmation model. So, for example, in a handle event, we can programmatically trigger a confirm, and this is going to show a model with confirmation on the page. And then we just specify a function which you want to run when the user confirms the choice. This is particularly nice when you want to show the confirmation conditionally, like user presses an action, and you want to check some state of the live view and either show the confirmation or not. And the second cool part is that if you have a bunch of items on the page, and you want to show a different confirmation message for each of them, for example, including the item name, putting this description as part of the markup up front means you need to duplicate a lot of information on the page, in the HTML. So doing this kind of lazily after the operation is done, it means we only show this single confirmation model. So if it is something that you may find useful, you can have this module. It's kind of all encapsulated in there. And finally, there is one pattern which we use both in Livebook and in Livebook Teams server, which I find really neat. And imagine you have a cluster deployment of multiple nodes, right? A usual Phoenix application. And now you want to have a process like a gen server, which runs only in a single place, in a single node. This could be some periodic, check, something like a job, basically, that runs periodically. And you don't want to duplicate that across all of the nodes, right? So there is a very straightforward way to implement that using the OTP primitives. And the way we can do it is we have a local supervisor on all of the nodes. Under the supervisor, we have a gen server watcher. And then when the watcher starts, we are going to try to start the global process under the same supervisor. The important part is that this global process needs to have a name using the global namespace. This ensures that we can only start one such process in the whole cluster. So now we either successfully start this process on our node or it's already running. In both cases, we start to monitor it. And this way, when this process crashes or the whole node is scaled down, all of the watchers are notified, so they go through the same procedure again and restore the process on one of the nodes. And yeah, that's all I have, and I'm happy to answer any questions.
OK, thank you so much. I see we have one question in the app, so I'm just going to read it right now. One of my biggest barriers to using Livebook has been having to edit code in the browser. I have my ideal typing setup in VS Code, Vim, shortcuts, AI autocomplete, etc. And it's quite painful stepping outside of that. Is this a fixed problem, or do you think more forms of integration might be possible?
Yeah, so this is a problem that keeps being brought up. We do have Vim and Emacs support in the configuration. You can set that, and we also try to bring as much IntelliSense into the editor itself. But now that kind of more code is being written by AI, we start to kind of think about different possibilities that we could incorporate that into Livebook. One approach which we've been briefly exploring is to actually have some AI assistance in a notebook. But this kind of doesn't really solve the problem if you are having an existing editor. So another approach that has been explored is to have kind of an MCP server and be able to connect Livebook into the editor and let the AI agent edit the notebook. And this has been explored as a package that you can use. I don't really remember the name. Yeah, Live Tools. So you can have a look at that. But we are aware of the problem, and we want to kind of explore those solutions and bring them back natively to Livebook. It's just that not something that we have done already. Yeah.
OK, we have one more question.
Hi. Would it be possible to implement the Elixir as a kernel for Jupyter, and that would solve the like give more adoption?
So sure. I believe there is an Elixir kernel for Jupyter. It was actually present when we started Livebook already. The thing is that we specifically wanted to build Livebook from scratch as our own take in order to solve a bunch of problems in Jupyter. So even in the Python ecosystem, people are aware of Jupyter shortcomings, especially regarding to kind of state management, that there is a global state, you run code in different order, and the state keeps changing, and this makes the notebooks not reproducible. So there's been like papers on this subject that claim that most of the notebooks online are not even reproducible. Anyway, there has been a lot of like cloud services in the Python ecosystem, and now there is a more recent project which is open source with another take. But again, we didn't want to go with Jupyter, but rather write it in Elixir so that it solves some of the problems, and it's also specifically tailored to Elixir, so we can kind of do things that make sense for us, take the trade-offs that make sense for us.